In 2018, Malaysia took in over 750,000 metric tons of plastic waste imports from over 19 countries, causing the government to place a temporary ban on the import of plastic waste. A total of 139 illegal plastic waste recycling factories have been shut down since January 2019 as they failed to meet the local environmental legislation. New plastic consumes approximately 5% of total oil production and is expected to reach 20% by 2050, resulting in a 15% raise of the global greenhouse gas emissions. The disposal of plastic waste causes marine, land and air pollution. Therefore, it is crucial to figure out what to do with the accumulating plastic waste, and perhaps plastic circular economy could be the solution. As such, people begin to become aware of this issue and promote plastic recycling. The most common plastic recycling method is mechanical recycling. However, plastic degrades when subjected to heating and shearing, so it can only be recycled up to 7 times. Besides, each type of plastic is sensitive to its own processing temperature. Therefore, detailed and labor-intensive sorting is required. These factors have restricted it to meet the basis of circular economy. As most of the plastics have high carbon content ranging from 60 to 90%, they can be a very promising feedstock in producing valuable chemicals through chemical recycling. Steam gasification is one of the best known technologies in chemical recycling. It is the partial oxidation of heterogeneous plastic waste with steam at high temperature. This produces syngas with high calorific value and minimizes the production of tar and char. The process begins with feedstock preparation by sorting and shredding mixed plastic waste. The dried carbon-rich residues are fed into the first bubble fluidized gasifier with circulating sand as the heat transfer medium at 700 degrees Celsius. The gas produced further reacts with steam at 1500 degrees Celsius in the second gasifier, and up to 92% of carbon is converted into syngas. Char produced are oxidized in situ, thereby providing the heat required to achieve the high operating temperature. Tar is treated and removed in scrubbing towers as they foul the catalyst surface. The purified syngas then undergoes copper-catalytic reaction in a shell and tube isothermal converter at around 50 bar and 230 degrees Celsius to produce methanol. The methanol produced is pumped into a dense phase fluidized bed reactor with silico-aluminophosphate molecular sieve at 300 degrees Celsius. Inline coke combustion is necessary to improve the ethylene selectivity. Finally, the olefins produced undergo polymerizations to produce the new plastics. With a total of 27,000 tons per annum of plastic inputs, 9,000 tons per annum of saleable plant output, 6,000 megawatt hour per year of on-site electricity generation, and 33% of overall process yield, it is estimated that such plant on an annual basis will spend a total cost of 20 million Malaysian ringgit that can be compensated by a total revenue of 48 million Malaysian ringgit, generating a total operating income of 28 million Malaysian ringgit. The data shows that this process has net greenhouse gas emissions of 1000 kilograms of carbon dioxide per ton of mixed plastics. This has been proven to reduce the emissions of incineration by 46%. Chemical engineers conduct analysis on the carbon value of plastic waste and maximum allowed contamination level to determine the feasibility of chemical recycling. In addition to that, further research for the regeneration and reuse of cheap catalysts is necessary to reduce the process cost, improve product quality, as well as enhance the overall process optimization. Chemical engineers are also responsible for the detailed chemical characterization of end products so that the recycled plastics are competitive with virgin plastics and the waste streams are able to fulfill the local regulations. To sum things up, the gasification of plastic waste is a scalable and promising technology in the plastic circular economy. It produces syngas which can be used to make high-quality new plastics. It saves pretreatment costs as it is relatively tolerant to contamination. The design of the dense phase fluidized bed reactor prolongs the catalyst residence time, thus improving the overall conversion. Chemical engineers are important in further developing such chemical process plant so that it can be fully commercialized in the near future.